Hey students, welcome back. We are going to learn today about elements and compounds under section 2.3 in your chemistry. And as always, I got my buddy here, Beethoven, going to keep an eye on me. Let's adjust his, make sure he's COVID safe there. There we go. All right, so there he is with me. So what we're going to learn is talk about compounds and elements. What's the difference between them? So things like sugar. Take some sugar and some you might take some sugar and you might take some cup of cream and you might take some food coloring. Okay, you make this concoction and you will make cotton candy. So that are several compounds coming together, making another compound. So we're going to talk about today is how are elements different from compounds and how are compounds different from elements? Are they a part of one another? Are they completely separate? How do you determine what they are and tell them apart? So that's what we're going to talk about today. So elements is the simplest form of matter. And what I mean by that is it cannot be broken down any further into something else. So something that is an element, it has a unique set of properties to it that no other part of matter has. That's an element. A compound is the substance that will contain two or more elements that are bonded together, chemically bonded together. All right, so for instance, we had our aluminum nails and our iron nails that we talked about last time. Those weren't chemically bonded together. That was not a compound, that was a mixture. So a compound is two or more elements that are chemically combined in a fixed proportion. And we'll talk about those fixed proportions later, but they're chemically bonded, is what you need to remember. Okay, so compounds can be broken down into simpler substances by chemical means, but elements cannot. I can break a compound into smaller parts, which would be elements, but an element, if I break the element and down, it'll still be that element. Okay, so breaking down compounds. Okay, a chemical change is something that produces a change when something changes in the matter. So if I apply some sort of process to the compound, it changes the composition of that compound forever. Okay, so for instance, when sugar is heated, it goes through a series of chemical changes. So this white or brown sugar is heated, and the compound that makes up sugar, carbon, hydrogen, oxygen, will change, and you'll see this black material, that's carbon. You might see some evaporation of some liquid, and that is some water that comes off of this sugar. Okay, so this sugar has been chemically changed, it's been broken down, and it's irreversible. Okay, so here's one right here, the final product. So here we have sugar. This little arrow right here means that's where the chemical reaction is going. It's called the yield arrow. Okay, and then what we have here is that what makes that is heat. And the products on this side, the right side of the equation is called the products. We'll have carbon and water. And so right here is the carbon, and you might see some water evaporating. Another one would be if you want to split water in two. We'll do a lab a little bit later in the year when we take a 9-volt battery, put some wires from that 9-volt battery into water. Using electricity, we will yield hydrogen gas and oxygen gas. So this water was bonded together in a compound chemically, and we break those bonds into hydrogen gas and oxygen gas. So what you need to know is that compounds can be broken down into smaller elemental parts, if you want to think of it that way. All right. So properties of compounds can be different from their component elements. Okay. Things like sodium and chlorine by themselves can be quite dangerous. When you combine them chemically to form sodium chloride, which is just salt, it's pretty harmless. So, for instance, chlorine will kill organisms in pools as a gas. If we breathe that, it'll kill us. That was the gas that was used in World War One to kill, and literally, you breathe this in, it dissolves your lungs, and you literally drowned in your body. It's a horrible way to die. But chlorine as a gas is very dangerous. Okay, sodium. If you put sodium in water, it instantly reacts and it looks like a firework with all these sparks. If you drop a little clump of this kind of gray clay, kind of looks like gray clay, and you cut it and you throw it into some water, it'll spark because it wants to react. So, but sodium is a great source of light. It's not so common any longer with the addition of LEDs into our lives, but street lights used to have sodium stored in oil to keep them from reacting with oxygen and water because sodium really wants to react. And that sodium vapor produces a very, very high lume light. So some street lamps may still have those in some towns. Okay, so sodium can be a pretty dangerous, or at least a very reactive um, element, and so is chlorine. But when you put them together, they're basically harmless and yummy. Salt on our pretzels, salt on our food, salt on our roads during the winter for ice, salt to preserve things, and say if you're pickling something. So salt is a very useful compound, but in its elemental form, sodium and chlorine are very reactive and can potentially be very dangerous. So, how do we distinguish substances and mixtures? So, the rest of this time together, we're really talking about this. How can we talk about the differences between a substance and a mixture, and what is the composition of those? So, here's a very helpful flow chart that we'll spend the rest of our time on, and have matter. Okay, you start with matter. So, matter is anything that takes up space and has mass. Anything that has mass and has volume is matter. And matter can be in two forms. It can be a substance. A substance means that it is a homogeneous, it is the same throughout. So, two types of substances could be a compound like salt. An element, the two elements that make it up could be sodium and chlorine. Okay, sodium chloride. So, a compound is made of more than one element that can be chemically separated into its elemental form. So examples of that would be beryl is a mineral that contains several different elements in it that makes up this gem called beryl. But then silver is an individual element. And if you can't break silver down into any other components. So a substance here, up here on our flowchart, substance is homogeneous, the same throughout. Beryl is the same throughout, and so is the silver. Okay. Now a mixture. Here's a mixture. A mixture can be vary in composition. Okay, and that can be physically separated. So, like if you had sand, gravel, salt, and maybe some leaves, you could physically separate those into their various parts, right? You have the gravel and the sand and the salt and the leaves. You could separate those either by a sieve or you could do it by hand. So a mixture can be separated, much like we were talking about the other day with oil and vinegar. They would separate. Okay, you can separate. They can be separated. Okay, it'd be separated into their pure substances: vinegar and oil, gravel, sand, and leaves. They are all substances. Okay, so they can be separated physically into substances. Those are then compounds that can be broken into elements. Okay, so that's some of the flow chart. If it cannot be physically separated, it's a mixture, a homogeneous or heterogeneous mixture. A homogeneous mixture is uniform throughout. It's called a solution. Okay, a heterogeneous mixture is not uniform throughout. Some examples of that would be steel. Steel is a homogeneous mixture. When I say a homogeneous mixture for steel, steel is made up of carbon and iron. Carbon and iron. So anywhere I would take a sample of the steel saw blade, I would have the same concentration or same ratio of the number of carbon atoms as I would iron atoms throughout. So it's homogeneous, it's thoroughly mixed. You could think of it that way. Now, a piece of granite is made up of several different minerals: quartz and feldspar and biotite and olivine and all these different types of minerals, dark and light. So you can even see on this piece of granite that there's more light minerals right here, the quartz and maybe the feldspars. Then over in this section here, we have the darker minerals, say biotite and olivine, different types of minerals. So if I were to take a sample from here, I'd be more dark minerals, and over here would be more light minerals. So this is a mixture. These are both solids, but one is a mixture that is heterogeneous, not uniform throughout, and the stainless steel, iron, and carbon are uniform throughout. So let's just look at a problem here, okay? A little conceptual problem. We have a blue-green solid in the photograph, okay? Whatever this blue and green material is, okay? It's like a powder, okay? And we heat it up And when we heat it up, we have a gas that comes off. It has no color to it, and a black solid. So all three materials are substances. It is it possible to classify any of these substances as elements or compounds? All right. So we have the blue green solid. Okay. So we can tell that that is a compound. That is a compound. It can be broken down into similar parts. A compound can be broken down into similar parts. How do we know that's a compound? Because it was broken down into a gas and to a black solid. So it contained at least something that was a gas when it was heated, and something that was black when it was heated. So it was least contained of those two things. So we know that the blue green solid is a compound because it can be broken down. But heating caused that chemical change. But we don't know for sure what the black solid is. Is that a compound, or is it an element? We don't know. We'd have to do further testing. We'd have to see if we can continue heating up the black solid. Does it continue to change as we heat it? The same with the gas. So we can say that the blue-green substance is a compound, but we can't say if the colorless gas or the black are clearly elements. All right, last thing we'll talk about today is formulas and symbols. Symbols have been around for a long time, and we use from early days and this, before 1700s for sure. Things like lead and salt and zinc and gravel and tin were these were the symbols used by alchemists. And then Dalton, which was the scientist that really pushed forward chemistry after Lavoisier. There's some symbols he used for different elements: gold, oxygen, carbon, and zinc. But here are the common symbols. Most, if not all, elements that were discussed and talked about by scientists pre 1700 were used. They used Latin, just like they used Latin in biology to describe a genus and species of an animal. Like we humans are Homo sapiens, that's Latin. They used Latin to describe the sodium, potassium, antimony, copper, gold, and the like. And so these symbols are not English letters, they are Latin. So sodium, even though it doesn't have an N or an A in it, it's natrum. That's the Latin name for it. Silver is argentum, comes after the word silver. Argentina comes from that word, same Latin word, because the conquistadors that were going to the new quote unquote new world thought they were going to find rivers and mountains of silver. So they named the now country in South America Argentina. After silver. Okay. Iron is ferrum, something that is ferrous, has iron in it. Plumber used to a plumber. A lot of lead, a lot of pipes are made of lead till most recently, maybe 20 so years ago. So this idea of a plumber works with plumbum, which is lead. So these are just things we'll be talking about more about symbols and how you can learn them and how you can memorize them and get used to using them later. But these are the Latin symbols that were used early on. So that's the end of this lesson. And I hope I'll see you soon. Go ahead and watch this before our next class, and I'll talk to you soon. Bye.